Okay, you should write on your assignment 6.4, day 53, because today we're gonna split an atom. We're gonna use that to make a power plant, and you're gonna explain all of that. Every year my students say that this was the most sciencey thing. And because I've been doing this for a long time, I can assure you it's possible. I have taught students that were very, very challenged, academically speaking. And I have seen students who otherwise wouldn't do great in science classes do fine on this content. I should probably mention that my father worked at a nuclear power plant when I was a little boy. So I kind of grew up with nuclear physics, and I know that you can learn this. I'll help you. I got it, I swear. I've been doing this for years. We're going to do the vocab along the way. You've already had the band-aids. We're going to review that. Then we're going to talk about uranium and uranium stuff, and then we'll get to that reaction in the reactors, okay? We talked already about atomic number, atomic mass. Protons make it a specific element. Neutrons are basically just baggage. So when you look at the periodic table, those numbers mean something. You'll notice that the number at the top grows by 1 because every set of protons has a name. 5 protons is called boron, and 34 is called selenium. Okay. We also talked about isotopes, which are just versions of an element. So if you've got carbon with its 6 protons, then you could have carbon 12, which has 6 protons and 6 neutrons, or carbon 13, which has 6 protons and 7 neutrons, or carbon 14. They're just versions. They're like the light one and the medium one and the heavy one. How much cargo do they have? Technically, you can have even lighter carbon, carbon 11. You might be able to stabilize carbon 15 for a second. But remember that some combinations are not as stable. We talked about the atomic weight, which is the average of the isotopes. That's why most atomic mass numbers in the periodic table have a bunch of decimals, because you're actually averaging isotopes. And we've talked about uranium. Uranium has 3 common isotopes on Earth. We're only going to discuss 2 of those. Uranium-234 is rare and kind of irrelevant. So we're going to talk about uranium-238, which is stable and useless. And we're going to talk about uranium-235, which is nuclear fuel. We also defined radioactivity already. That's the process of an atom falling apart. So if you've got an atom that's not too stable, it will lose a part, or it'll split, giving off energy. And those parts that fall off are called radioactivity. Technically, there's different types of radioactivity depending on which parts fall off, but we don't need to know that because this is AP Environmental Science, and that doesn't really matter for us. Okay, good thing, good thing. Uranium special. It's right on the edge of what's possible. It's about as big as you can make a nucleus before it falls apart. Anything bigger, if you get one larger than uranium, we call that plutonium, and that's unstable. That doesn't really hold up on our planet. So what's cool about uranium is it's right on the edge of what's possible. You can push it over the edge. Uranium is right there where you can force it to fall apart, because uranium-235 is pretty stable on our planet, but uranium-236 inherently unstable. So we're going to do that. That's where we start today. We're going to split an atom. This is called fission. That's a vocab term you should know. Fusion is technically possible, making an atom, or I guess combining atoms to make a bigger nucleus. That's called fusion, but that's outside the scope of apes. We don't need that for this class. So we're just going to talk about number 36 and number 38 today. 36 is about the reactors, and that means you have to know about the reaction. Number 38 is about the fuel. Let's talk about that fuel really quick. We're going to start the fuel, and we'll come back to the fuel later. If you picked up a chunk of uranium, it would be 99.28% uranium-238 and roughly 0.72% uranium-235. And that's not enough. A rock of uranium is not useful. It's just ore. And so there's this process called enrichment. It's a vocab term that you should know. Enrichment is taking that rock, which is mostly useless, and making it more useful. You can enrich uranium to the point of being nuclear power plant fuel. That's about 3%, 235. You can see in my little diagrams at the bottom of the screen that the red has grown a little bit. That's for a reactor. That's called reactor grade or fuel grade. And you can keep going. You can get rid of almost all the 238 so that you're left with almost pure 235. That's how you make weapons. That's weapons grade uranium. So the process of enrichment is getting rid of the 238 so that 235 is more common. And it's not like you can pick atoms. You can't grab 235 from the rock. Instead, what you can do is make it into a gas. Crazy chemistry to do that. You grind it up into powder and you make it into a gas. And then you spin that gas really, really fast. Do you all know what centripetal force or centrifugal force is? Like if you put water in a bucket, you can spin it around, and if you spin it fast enough, the water will get smashed into the bucket as you're spinning it. So you use these machines called centrifuges. You spin that uranium gas, and the heavier stuff goes to the bottom, and you can just kind of shave that off and throw it out. And then you grind it up and you make it into a gas and you spin it in a centrifuge, and the heavier stuff goes to the bottom, and you shave that off and you throw it away. So what you're doing is you're separating them momentarily, and then you're sorting them so that the heavier stuff goes to the bottom of the centrifuge tube, and then you throw that out. You don't have to be an expert on how that works, but it's probably worth knowing that enrichment is getting rid of the uranium-238. So what you're left with has a higher concentration of 235. You're raising the percentage of uranium-235. You should know that. I mean, imagine theoretically that I only wanted to teach redheads. We all know that redheads are an abomination of nature, but anyway, that was a joke. Let's imagine that I only wanted to teach redheads, but I'm just a teacher. The students that show up in my room are the students that show up in my room. If I couldn't pick who comes into the room, and I only wanted to teach redheads, I could find a way to flunk all the other kids, right? If I could just kick out the ones I don't want, I'm left with 100% redheads. I can raise my concentration of redheads by excluding the parts of the sample that I don't want. That's enrichment. So you can't pick out uranium-235. You're just going to get a rock. But what you can do is you can orient the uranium so that the stuff at the bottom of the tube is mostly the unwanted, and then you throw that out and you're left with a higher concentration of the light isotope. You got to do this a lot. In that little image, you can see a room full of centrifuges. That would be required to make a single power plant, and that room would have to work for, I'm assuming, years. It's a tough process. Uranium is just a rock, by the way. You can dig it up in the ground. You can probably dig it up in Montecito right now if you want to go dig a hole. Anyway, enrichment is the process of getting rid of the 238, so you have a higher percentage of 235. And you can pack that powder into these little shapes. Those are called fuel pellets. And then you can stack those pellets in tubes. Those tubes are called fuel rods. And then you can bundle all of those fuel rods into this thing called a fuel assembly. So it's a thing with a bunch of tubes that are all stacked with little pellets. And then you can put that assembly inside of a reactor core. And that's where we're going to make nuclear reactions, and that's how we're going to make nuclear electricity. We're going to run coolant over that fuel assembly, and it's going to leave heated. You can see that on the screen right now. That's a reactor core. It has a fuel assembly, which is a bunch of fuel rods, which has a bunch of fuel pellets, which are enriched uranium. And voila, we're ready to do nuclear reactions. But I'm going to pause here, maybe see you back in class, and then we'll come back to do some nuclear reactions. We have enriched fuel, and we've built a core. So that's mostly study goal number 38 with a little bit of 36. I'm going to take a break for a minute.